Section 8.4, we're going to talk about these relationships among all of our trigonometric functions. This fun little section, we're going to start to develop some simplifying of our trig functions. We get to take a look at our trig Pythagorean identity and how that spawns off other Pythagorean identities and co-function relationships. So there's a lot of information in this section. So let's get started. First thing we're going to do is do a little rehash of what we've talked about already, and that's our relationship with reciprocal functions. Remember that we have our reciprocal functions of cosecant and secant and cotangent, and that they are the reciprocals of our sines and our cosines and our tangent functions, 1/overs. So that's a little review from section 8.2. What about negative rotation angle-wise versus positive rotation? So here we have our odd-even identities. So a lot of these first two slides here, a lot of just information, not so much doing any examples per se. So based on our all support the covers ASTC, where we have positive values of all trig functions in quadrant 1, sines and cosecants are positive in quadrant 2, tangents and cotangents are positive in quadrant 3, and cosines and secants are positive in quadrant 4. What happens when we rotate as a negative angle versus a positive angle? Remember that positive angles go counterclockwise and negative angles go clockwise. So when you have a sign of a negative angle rotation, you're thinking about where that angle puts you. And these angles, by the way, we're talking about these as a reference angle. We're going to be talking about between 0 and 90 degrees for this even-odd identity. So if I rotated negatively, I'd be putting myself into quadrant 4. And if I rotated positively, I'm putting myself into quadrant 1. And so in quadrant 4, we know that sines are negative, as are tangents. But cosines and secants, when you rotate into quadrant 4, remember that that's a positive cosine quadrant. And so that's why in a negative angle rotation for cosine, you still have positive value of the cosine, or positive value of the secant function. So here it is, the very first of our identities. This is really the main one. If I can memorize the Pythagorean identity here, of the one we're going to show you, I can develop the other ones that come from this. So let's talk about where the Pythagorean identity comes from. First of all, Pythagorean, we're talking about a right triangle, obviously. That right triangle is the triangle that results as we move our point around our unit circle. And so we've already taken a look at sine is equal to y over r, and cosine is equal to x over r. Well, if I solve each of those respectively for y and x, I would get that x is equal to r cosine theta, and that y is equal to r sine theta. Then, if we took Pythagorean, x squared plus y squared equals r squared, and we just simply substituted our r cosine theta in for x, and our r sine theta in for y, then we would get the second line of the proof for our Pythagorean identity. We square both of those values, so we get an r squared cosine theta, an r squared sine squared theta. And in the next fourth line, you'll notice that what we do is we factor out from these two a GCF of r squared. And then if I simply took that and divided everything by r squared, we would get our Pythagorean identity. Cosine squared theta plus sine squared theta equals 1. Now from that, we can develop these others. There are 10 other Pythagorean identities. So here's the one that we just came up with. And from that, we can develop these other ones. Now, let's look at the ones directly below it, these guys down here. These, sine squared theta equaling 1 minus cosine squared, or cosine squared equaling 1 minus minus sine squared. Those just come from simply moving sine squared or cosine squared to the other side of the equation. All right, what about, though, going this way? How did we take this and develop this equation and then subsequently the ones below? Well, what we did here is I took the cosine squared theta, sine squared theta equal 1, and I'm dividing it out by one of those trig values. And to end up with a tangent, remember, is a sine over a cosine. And that means if I wanted to end up with this 1 plus tan squared theta equals secant squared theta, that would have meant I divided this original Pythagorean identity by cosine squared theta. And if I did that, 1 over, or cosine squared over cosine squared produces the 1, and sine squared over cosine squared produces the tangent, and 1 over cosine squared produces the secant. And then from those, again, manipulating, subtract 1, and I get the next Pythagorean identity. Or maybe instead I subtract secant squared and move 1 to the other side, and I get that identity. Or maybe I subtract tangent squared, and I get that identity. What about taking the original and somehow coming up with this set and its subsequent identities? Well, this time we divided by sine squared. Sine squared divided by, or cosine squared divided by sine squared gave me the tangent squared. And sine squared divided by sine squared gave me the 1. And 1 divided by sine squared created the cosecant squared. And then again, manipulating, moving things around to get those other 3 trig identities. So really, you don't have to memorize all 11. Just memorize this one. Just get this one down, and then know how you can manipulate it, and that's how you can create these other ones. So my suggestion would be, know that one, and whenever you're simplifying trig functions, put that on the top of the paper, and then you can just kind of see how you would adjust it to fit the given situation of the problem you are trying to simplify. So let's try a few of these. One more discussion on relationships is this idea of a cofunction relationship, also known as a complementary relationship. And here we have our right triangle. And this right triangle is made up of 2 acute angles, theta, and then some other angle that would have to be 90 minus theta. Because all the 3 angles of the triangle add up to 180. We already have a right triangle, which means that's 90 degrees. The other 2 have to add up to 90. So what does this cofunction relationship tell us? Well, it tells us that if I was sitting at the theta angle, and I took a sine of that angle, so if I took the sine of a theta, I would have the opposite side over the hypotenuse. Well, a cofunction relationship means that the value that I get there would be the same value, that ratio value would be the same thing as if I were sitting at cosine of the other acute angle, 90 minus theta. In that case, I have an adjacent over hypotenuse. And the relationship is that for the 90 minus theta angle, this O is actually the adjacent side. And so I get the same answer. Let's put some numbers in here that we're probably familiar with to actually see how this works. So if I said sine of, well, what angle produces a ratio of 1/2? We said for a sine, that would be a 30-degree angle. But there's also a cosine angle that produces a ratio of 1/2. And in that case, we have this being equal to 30 degrees. This one would be then 60 degrees. And where does 60 degrees come from? 90 minus 30. So that's the cofunction relationship. The other thing that might be worth mentioning here is this idea of the prefix. We have co here. So we have a sine and a cosine. They go together. A tangent and a cotangent. A secant and a cosecant. So that's how we know which ones go with which. And really, probably just need to know these three, because you can develop the other three, again, simply by switching the function that's with the 99 theta. All right, so those are our co-function relationships. Well, let's get to some simplifying. So our very first thing here is we're going to do a little review on some complex fraction work, because a lot of times we simplify and we end up with some complex fractions. Make some room here. In this case, we've got a t minus a 1 over t all over a t plus 1. So we have a complex fraction here. One thing that we can do is work with trying to make the numerator a single fraction, and the denominator is already a binomial. It doesn't have to become a fraction. It could be a fraction if we think of it over 1. So one method would be, we'll call this method 1, is to just make the numerator and denominators both single fractions, or a fraction in a binomial term or a monomial term or something. So let's try that here with this t minus 1 over t. T needs to get multiplied by something on the top and the bottom, so that I get to become a denominator of t, like it's buddy over there, 1 over t. Well, I need to have a t in the denominator, which means I need to multiply by a t on the top as well. So this whole thing then simply becomes a t squared minus a t, or a 1. And because now the denominators are the same, we can just write it all over t. And then we still have over binomial t plus 1. And at this point, when you're dividing a fraction by another fraction, or a fraction by a binomial part, or an integer part, this is where we save, change, and flip. So we save the top fraction, leave it as it is. We change multiplication, the division bar, we change this to become multiplication. And we take the denominator and we write it as a reciprocal. So 1 over t plus 1. Well then, let's take this, and let's move it down here. T squared minus 1 is a difference of 2 squares. So we can write it as t minus 1 times t plus 1 all over t times 1 over t plus 1. And now we see that we're multiplying. We've got some factors here that can cancel. T plus 1, t plus 1. And we end up with a t minus 1 over a t, which we could simplify even further, because this is the same thing as t over t minus 1 over a t, which we know is 1 minus 1 over t. All right, so a little review there, a little algebra review on complex fractions. So how does that work when we're simplifying trig functions? It's the same idea. Couple different approaches to simplifying trig functions. If you happen to see a part of your trig function, your original expression, that looks to have some Pythagorean identity parts in it, something squared plus or minus a 1, or just something squared, then we probably want to try and go and use Pythagorean identity routes and simplify from there. Another way is, as in the case here for b, we don't see any Pythagorean identity. But what we do have is just a sine and a cosecant. So the other thing is to generically approach these problems. Maybe you want to just try and make everything in terms of sine and cosine. So if we do that, if we simplify this, I have a 1, and we're going to keep sine x as sine x, but a cosecant, remember, is a 1 over a sine x. Well, look at that. A sine x times a 1 over a sine x just simply means I get a 1 down there. And so that whole thing simplifies to just becoming 1. That's a pretty straightforward expression that we can simplify, but they get a little more complicated. So let's see how this next one's going to look. So now we end up again with a situation that looks like a complex fraction. Again, don't see any squared terms, just see a bunch of signs and some ones and negative ones. So in this case, we're going to try and make out of the numerator, we're going to create a common denominator up there and see if we can write this thing as a brand new single fraction. So I start out with a sine theta, and I want to manipulate it so that I end up with a denominator that's the same thing as the 1 over sine theta, which means down in the denominator, I want this to become a sine theta, which means on the top has to multiply by sine theta. Again, by doing that, you're multiplying by 1. You're not changing the problem, just changing the way that it looks. And all of that would still be over sine theta plus 1. So, sine squared theta minus 1 on the top over sine theta. There's the top fraction of my complex fraction. And then I have sine theta plus 1. And now we save, change, and flip. Save sine squared theta minus 1 over sine theta. Multiply now by 1 over sine theta plus 1. Got some difference of squares going on right there, which means we can factor that thing. That becomes sine theta plus 1 times sine theta minus 1 all over sine theta. And then still multiplied by 1 over sine theta plus 1. And here we again, we have some common factors, the numerator and denominator, that get to cancel each other out. Then what do we end up with? Well, we end up with a sine theta minus a 1 all over a sine theta. But we want to see if we can simplify this further. And we can. This becomes sine theta over sine theta minus 1 over sine theta. And that becomes 1 minus cosecant of theta. And now we're simplifying. That's as far as we can go for that problem. Fun stuff. All right, let's pick up the rigor just a little bit more. Sine theta, secant theta, cotangent theta. Again, don't see any squared things. I don't see any Pythagorean identities. So we're going to go ahead with the whole idea of let's make everything sine and cosine. So a secant is a 1 over a cosine. And a cotangent is a cosine over a sine. Well, look what happens here. Common factors cancel, and this whole thing just equals 1 again. Nice. What about B? All right, there are a few things that I see going on here. First of all, I see this 1 plus tan squared thing. That probably came from some sort of one of our Pythagorean identities. The other thing I see here is this relationship of this angle theta, we'll call that whole thing theta, which is an x minus a 90 degrees, and that reminds me of our complementary or our co-function relationships. All right, so I want to be thinking about that now as we solve this problem. So where do we start? Well, this is what I would encourage you to do with this problem is, I said to put on top of your paper or something the Pythagorean identity. And then figure out how in the world did this get manipulated to become a 1 plus a tangent. Well, a tangent results when I divide everything by a cosine. So this becomes a tangent squared theta plus a 1 is equal to a secant squared theta. And if I look and notice that 1 1 plus tangent squared is what I've got right there, well, then we can write that, instead of a 1 plus tangent squared, we can write this thing as a secant squared of x minus 90. Okay, but then let's think about this cofunction relationship. I'd love for it to be 90 minus x, because that's what our cofunction relationship looked like. They were something with 90 degree minus x. By the way, those could be pi over 2 also in radians, but we're just looking at degrees. All right, so I have a x minus a 90. I want it to be a 90 minus x. If I look at those two, I notice that they're opposites of each other, which means I can factor out a negative. So why don't we take our secant squared, and we're going to pull out a negative. I'm going to have a negative x plus a 90 degree in there. And that becomes secant squared a negative of 90 minus x. Oops. Minus 90 degrees. Sorry about that. I mean, it should be positive. All right, so we get that. I have that cofunction relationship of 90 minus x. I like that. Then the next thing we can think about is, all right, we're squaring this angle. And when I square that angle, whether it's positive or negative, I get a positive solution. So really, secant squared of this angle negative 90 minus x could be thought about like this. Secant of the negative 90 degree minus x squared. If that happens, it becomes a positive angle. And it just becomes secant squared of 90 minus x. Well, that's good, because that is one of my cofunction relationships. Which one is it? Well, let's back up one. And we see that a secant of 90 minus an angle is equal to a cosecant. So in that case, what we have here is actually the equivalent of a cosecant squared of x. And there we are. What about this one? This next one here. I see a cube, don't see a square. So let's go ahead and just approach everything in terms of sine and cosines. This should have said cosine x, by the way. So we can write cosecant, not cosine, cosecant of x. So we can write cosecant as 1 over sine x times, well, we got a cosine cubed of x. A tangent is a sine of x over a cosine of x minus a sine of x. One thing I noticed, inside of my brackets, I have a cosine x factor on the bottom. Cosine cubed now becomes a squared. So I could have a 1 over a sine of x. And now cosine squared x sine of x minus a sine of x. You're going to find that there may be a couple different approaches to the way we do these problems. In this case, you could simply distribute the 1 minus sine x inside of this bracket to everything. That's one approach. You could take the bracket and see that there's a common factor of a sine x and factor that out. Either way, we're going to go ahead and distribute. And if I did that, I have 1 over sine x times cosine squared x sine x, which means the 1 over sine x times the cosine squared x sine x. Those two get to cancel. And then I have a minus a sine x over a sine x after I distribute. So I get a cosine squared x minus a 1. And a cosine squared x minus a 1. Well, let's see. That looks like it might have come from our see, if I subtract a 1 to both sides, and then I subtract the sine squared to the other side, I'm going to get a cosine squared x minus 1, or in this case, this equals a negative sine squared x. All right, what about proving that we've got a 1 over a 1 minus secant a plus a 1 over 1 plus secant a is equal to the negative 2 cotangent squared of a. In proving, sometimes we work one side of the equation, sometimes we work both. In this case, I'm going to take the left side and see if we can simplify this and end up with the right side. So in this proof, we're just going to work the left-hand side. Hopefully I end up with a negative 2 cotangent squared a. Well, I should end up with that. So how do we deal with the left side? Well, I have two fractions, and they each have a different denominator. So we want to find a common denominator. And our LCD here would be a 1 minus a secant a times a 1 plus a secant a. So we take the original, and we're going to multiply that original, each of the original parts, by the missing denominator part of the LCD. What do I mean by that? Well, for the 1 minus secant a, it is missing 1 plus secant a to become a common denominator. So we're going to multiply the left side by 1 plus 1 plus. On the right-hand side, we have a 1 minus secant a that's missing from the common denominator. And so we multiply by 1 minus 1 minus. Over 1 minus. All right, so what happens here is now we have a common denominator of a 1 minus secant a times a 1 plus a secant a. So on the denominator, we know we're going to have 1 minus secant a times a 1 plus a secant a. In the numerator, we have a 1 times a 1 plus secant a, which is a 1 plus a secant a, plus a 1 times a 1 minus a secant a, which is a 1 minus a secant a. Well, look what happens with some of our numerator values. We have a secant a and a negative secant a. They cancel each other, end up with a 2 on the top. We have 2 over a 1 minus secant a and a 1 plus a secant a is a difference in 2 squares, which could be expanded into a 1 minus secant squared of a. And a 1 minus a secant squared of a, that looks like it probably came from one of our Pythagorean identities again. So sine squared, cosine squared equals 1. How do I create a secant? I divide everything by a cosine squared. So I get a tan squared plus a 1 is equal to a secant squared. And 1 minus secant squared, again, subtracting that to this one, subtracting that to this side, means I have a negative tan squared is equal to a 1 minus a secant squared. So we're going to replace our 1 minus secant squared with a negative tan squared. But wait, a negative 1 over tan squared is the same thing as a cotangent. So really what I have is this. 2 times a 1 over negative tan squared. And a 1 over tan is a, and here's our final proof, a negative 2 cotangent alpha. So there we go. We've taken the left side and we've proved that it is equal to, in case this problem, the right side, negative 2 cotangent squared alpha. There we go.